Hello, in this video we will do an experimental computer system which can do x divided by y and both x and y are positive numbers. We will take an example on how the division operation is done in the binary system. In our example we will divide 1111.101 by 101. The computer system will test the most significant bit. If it's larger than the denominator, then it will put 1 in the result, else it will put 0. And as you see, the most significant bit is smaller than 101, so the computer system has put 0. Then it will treat the most significant bit by multiplying it by 2 and then add it to the next most significant bit. The result is treated as previously. If it's larger, then the computer system will put 1, else it will put 0. And as you see, 11 is smaller than 101, so the computer system has put 0. Then this number is treated as previously until we will get a number that is larger or equal to the denominator. As you see in our example, 111 is larger than 101, so the computer system has put 1 in the result and then remove 101 from 111, and the result, which is 10, is multiplied by 2 and then added to the next most significant bit, and the same thing is repeated as previously. And as you see, 101 is equal to 101, and the computer system has put 1 and then remove that number from that number, and the result is 0. Then the computer system will multiply that result by 2 and then add it to the next most significant bit and repeat the operation for multiple times until we get a number that is equal to the denominator, and that number is removed from the denominator is removed from that number, and the result is 000, and 001 has been added to the result. Also, in our experimental computer system, the numerator is 16 bits number, which is 8 bits before the point and 8 bits after it. For example, the number 1011.1111 is represented in our computer system by adding 4 zeros before that number and 4 zeros after that number. The algorithm of our computer system is this. First, we will put the values of BTL, which is bits to the left, is equal to 0, NOR, which is number of ranks, is equal to 16, which represent 16 bits, DC, which is the counter of numbers or the ranks after the dot, which is equal to 2 to the power of minus 8, E, which is error, result, which is equal to 0. Then there will be the input of x and then y respectively. Then the computer system will test whether y is equal to 0 or not. If it's equal to 0, then it will output E, following the fact that any number divided by 0 is an error in the result. Then the computer system will test whether number of ranks is equal to 0 or not. If it's not equal to 0, then it will test whether the most significant bit is equal to 1 or not. Then if it's equal to 1, then BTL is equal to BTL plus 1, else BTL is equal to BTL. Then it will test whether BTL is less than y or not. If it's, then the result is equal to result multiplied by 2, else the result is equal to the result multiplied by 2 and the whole is added to 1, and BTL is equal to BTL minus y. Then BTL is equal to BTL multiplied by 2 and NOR is equal to NOR minus 1, and the computer system will rotate x to the left. After ending of the while loop, the computer system will multiply the result by 2 to the power of minus 8, then there will be the output of the result. And before we proceed, the operation result is equal to result multiplied by 2 is done in the computer system by shifting the result to the left and replace 0, and that operation, which is result multiplied by 2 and the whole is added to 1, is done by shifting the result to the left and replacing 1. The data path of our computer system is this. It's composed from a 4 to 1 multiplexer, 8 by 16 bits register file, arithmetic logic unit, shifter, an output gate, and a feedback loop to repeat the mathematical operations as needed. The control signals of our data path are shown. First, S1 and SO is to choose which value will pass through the multiplexer to the register file. WE is to enable writing a value inside one of the 16 locations of the register, or one of the 8 locations of the register file. WAA 210 is to choose which location from the 8 locations that the value will be written in. RAE is to enable reading a value through port A. RAA 210 is to choose a value from one of the 8 locations to read through port A. RBE is similar to RAE, and RBA is also similar to RAA 210, but the last two signals are through port B. ALU 210 is to choose an arithmetic operation to be done by the ALU. SH1 and SHO is to choose which operation is done inside the shifter. CLK are both the clock signals to change the status of the register file and the shifter with each clock cycle. OE is to enable outputting a value through the gate. The conditional signals can be get from the register file by putting one of the following circuits inside the location that we will save one of the following conditions, one of the following values. First, the computer system will test the value of y equal to 0 or not by putting OR gate in the location that we will save y, and that thing is similar to NOR. BTL is smaller than y is done by putting a comparator circuit in the location that we will save both BTL and y, or by taking a signal from the location of BTL and y and put it or enter it into the comparator circuit. Then the output is 1 if BTL is less than y and 0 if not. MSB is equal to 1 is tested by putting a buffer gate in the site of the most significant bit of X. Next state diagram of our computer system is shown. It's composed basically from 16 states. Each state will go to the next one by following the conditions. In the first state, which is state O, the computer system will put the values that we mentioned earlier. Then it will go to state 1. In state 1, there will be the input of X. After state 1, the computer system will go to state 2. In state 2, there will be the input of Y. Then, after state 2, the computer system will test whether Y is equal to 0 or not. If Y is equal to 0, then it will go to state 3, where the output of E will occur, and state 3 will go back to itself. Else, it will go to state 4. In state 4, nothing will happen, but after it, the computer system will test whether NOR is equal to 0 or not. If it's not equal to 0, then it will go to state 5, and in state 5 also there will be nothing, but after it, the computer system will test whether MSB is equal to 1 or not. If it's equal to 1, then it will go to state 6, and in state 6, the computer system will increase BTL by 1, but if it not, then it will go to state 7. And state 6 will go unconditionally to state 7. In state 7, nothing will happen, but after it, the computer system will test whether BTL is less than Y or not. If it's less than Y, then it will go to state 8, where the result is equal to result multiplied by 2. But if it's not less, then the computer system will go to state 12, where result is equal to result multiplied by 2, and the whole is incremented by 1. And the state 12 will go unconditionally to state 13, where BTL is equal to BTL minus Y. And both these states, which are 8 and 13, will go to state 9 without following any condition. In state 9, the computer system will multiply BTL by 2, and after this state, the following state is state 10, where the computer system will decrement NOR by 1, which will go to state 11 without following any condition, where the computer system will rotate X, and this state will go back to state 4 without following any condition. But if NOR is equal to 0, then the computer system will go to state 14, where result is equal to result multiplied by dot counter, and state 14 will go to state 15 without following any condition. Then there will be the output of result, and state 15 will go back to itself without following any condition. The next state table of our experimental computer system is shown. It's composed as similar to the next state diagram from 16 different states, beginning from state O, ending with state 15. After state O, the computer system will not test any condition, and it will go to state 1 unconditionally. After state 1, the computer system will go to state 2, and after state 2, the computer system will test whether y is equal to 0 or not. If it's equal, then it will go to state 3, else it will go to state 4, and the next state to state 3 is state 3 itself without following any condition. The next state to state 4 is two different states after testing whether NOR is equal to 0 or not. If it's equal to 0, then the computer system will go to state 14, else it will go to state 5. The other conditions are not important to this state. After state 5, the computer system will test whether MSB is equal to 1 or not. If it's equal, then it will go to state 6, else it will go to state 7, and the state that follows state 6 is state 7 without following any condition. Then the state that follow state 7 are two states, which are state 8 and state 12, depending on whether BTL is smaller than Y or not. If it's smaller, then the computer system will go to state 8, else it will go to state 12. After state 8, the computer system will go to state 9 without following any condition, and after 9, state 10 is the following state, and after state 10, the computer system will go to state 11 without following any condition. After state 11, the computer system will go to state 4, and after state 12, the computer system will go to state 13, and after 13, the computer system will go to state 9, and after state 14, the computer system will go to state 15, and after state 15, the computer system will return back to state 15 without following any condition.